Welcome to my 22nd tutoring session in A-level chemistry. In this video, you will learn about periodic trends in electronegativity. Please take a moment to watch my previous videos on topics sizes of electrically neutral atoms and charged ions, periodic trends in atomic size, effective nuclear charge, and shielding effect in group 2 elements. These videos will provide you with a better understanding of this video content. Link to these videos is given in the description below. Take a moment to watch those videos. What is electronegativity? Electronegativity is a measure of an atom's ability to attract a shared pair of electrons in a chemical bond. It is a relative scale developed by Linus Pauling, with fluorine being the most electronegative element assigned a value of 4, and cesium is the least electronegative element with a value of 0.79 in the periodic table of elements. Now coming to the periodic trends in electronegativity. Electronegativity increases as you move across a period from left to right in the periodic table, while the electronegativity decreases as you go down a group from top to bottom in the periodic table. Why fluorine with atomic number 9 is more electronegative than fluorine with atomic number 17? Why hydrogen chloride and hydrogen fluoride molecules have polar covalent bonds? Why hydrogen fluoride is more polar than hydrogen chloride molecule? Why oxygen with atomic number 8 is more electronegative than nitrogen with atomic number 7? You will find the answers for all these 4 questions by the end of this video. Now remember, electronegativity is a property of a bonded atom in a molecule. For example, chlorine atom in hydrogen chloride molecule and fluorine in hydrogen fluoride molecule. So electronegativity value can be assigned to atoms that are associated with other atoms by a chemical bond. So you cannot assign electronegativity values to isolated gaseous atoms that are not associated with other atoms by a chemical bond. So electronegativity is a property of a bonded atom. So electronegativity value can be assigned only to those atoms that are chemically bonded in a molecule. Secondly, electronegativity is a relative property on a relative Pauling scale of 0 to 4 and has no units. Now, electronegativity value is assigned to the elements in the periodic table based on a relative Pauling scale, and this Pauling scale is based on bond dissociation energy. Electronegativity cannot be measured but can be calculated. So based on atomic and molecular properties like bond dissociation energy. What is bond dissociation energy? It is the energy required to break a bond. For example, 432 kilojoules per mole of energy is required to break the HCl bond. So bond dissociation energy in case of HCl bond is 432 kilojoules per mole of energy. So Pauling scale is based on bond dissociation energy, and that is how the electronegativity values are assigned to the elements in the periodic table. Let me explain the concept of electronegativity with respect to hydrogen chloride molecule. In the hydrogen chloride molecule, you will find the hydrogen and chlorine atom are held together by a covalent bond. A covalent bond is formed by mutual sharing of electrons between the atoms involved in the bond formation. Now, in case of hydrogen chloride molecule, the electrons are not equally shared, rather they are unequally shared. Chlorine is more electronegative than hydrogen, and therefore it has a tendency to pull the shared pair of bonding valence electrons closer to itself, which is indicated by a arrowhead pointing towards chlorine atom. And as a result of this, the chlorine atom gains a partial negative charge, while the hydrogen atom gains a partial positive charge. This partial positive and negative charge, it is denoted or represented by a Greek letter delta, which means small. So chlorine atom gains a partial negative charge, while the hydrogen atom gains a partial positive charge. Now we have got a hydrogen chloride molecule with a positive end and a negative end. The crossed end will be the positive end and the arrow end will be the negative end. Hydrogen chloride molecule with a positive end and a negative end, and therefore hydrogen chloride molecule has a dipole, resulting in a polar covalent bond. Now hydrogen chloride molecule is a heteroatomic molecule where you find bond between two different atoms. So here hydrogen and chlorine are the two different atoms associated by a covalent bond and is polar in nature. Now what about homoatomic molecules? Homoatomic molecules like hydrogen and chlorine are non-polar in nature. So the covalent bond is non-polar in case of homoatomic molecules like hydrogen and chlorine, and the electrons are equally shared between the atoms involved in the covalent bond formation, and both the atoms held by covalent bond, they are identical with similar electronegativity values, and therefore homoatomic molecules are non-polar in nature. They have a non-polar covalent bond. Now you know the significance of arrowhead pointing towards the chlorine atom in the hydrogen chloride molecule, with the hydrogen atom having an electronegativity value of 2.1 and chlorine with a electronegativity value of 3.2. Why chlorine is more electronegative than hydrogen atom in the hydrogen chloride molecule? Let's find out the answer by examining the electron structure of hydrogen chloride molecule. In the hydrogen chloride molecule, you will find the 17 positively charged protons in the nucleus of chlorine atom with a greater attraction for the shared pair of bonding valence electrons than the attraction for the only proton in case of hydrogen atom. So the attraction for the 17 positively charged protons towards the shared pair of bonding valence electrons is greater than the attraction for a single proton of hydrogen towards the shared pair of electrons. And this leads to an unequally shared pair of bonding valence electrons, leading to a polar covalent bond. So that is to say, the 17 protons in the nucleus of chlorine atom, it pulls the or attracts the shared pair of bonding valence electrons closer to itself, and thereby creating a polar covalent bond. So the shared pair of electron is more towards the chlorine atom. So here the chlorine atom with 17 protons, positively charged protons, wins the tug of war, and hydrogen atom with a single proton in its nucleus is just a mute spectator to let go of its shared pair. Now the shared pair is not lost, it is there, but it is unequally shared. It is more towards the chlorine atom. And this is the reason why chlorine is more electronegative than hydrogen in the hydrogen chloride molecule. It has a stronger hold. Chlorine atom has a stronger hold over the shared pair of electrons. And same explanation can be given in case of hydrogen fluoride molecule. With 9 protons in the nucleus of fluorine atom. So the attraction for the 9 positively charged protons in the nucleus of fluorine atom towards the shared pair of bonding valence electrons is greater than the attraction for the only proton towards the shared pair in the hydrogen fluoride molecule. And that leads to a polar covalent bond in case of hydrogen fluoride molecule. So now we know that why hydrogen chloride and hydrogen fluoride molecules have a polar covalent bond. Now, among these two molecules, hydrogen fluoride molecule is more polar than hydrogen chloride molecule. Why is that? Let's find out. So electronegativity of fluorine is 4 as compared to 2.1 for hydrogen. So let's compare the electron structure of hydrogen chloride and hydrogen fluoride molecule. So in case of hydrogen chloride molecule, you find the chlorine atom with 2 shells, inner shells with a total of 10 core electrons. 2 core electrons in the first shell, followed by 8 core electrons in the second shell. Now, these two inner shells with 10 core electrons, it shields the nucleus from the shared pair of valence electrons. And there is increase in shielding. What is shielding? Shielding is a phenomenon where the inner core electrons partially block or reduce the electrostatic force of attraction between the positively charged protons and the shared pair of electrons. So here we have got 2 shells with core electrons, and each shell acts as a shield, reducing the electrostatic force of attraction between the positively charged protons and the shared pair of electrons. And as a result, even the Z effective or the effective nuclear charge is also low, or it decreases. What is Z effective? Now, effective nuclear charge is the electrostatic force of attraction between the positively charged protons and the outermost electrons, or the shared pair of electrons in a molecule. And what about the hydrogen fluoride molecule? So in case of hydrogen fluoride molecule, you find only one shell in case of fluorine atom. So if you observe the fluorine atom very closely in the hydrogen fluoride molecule, you will find it has only one inner shell with 2 core electrons. And these 2 core electrons present in the first shell, it shields the nucleus from the shared pair of valence electrons. So shielding is, or the screening effect is very less in case of hydrogen fluoride molecule. So there is only one shell which is shielding the nucleus from the shared pair of bonding valence electrons. And as a result, the effective nuclear charge is more or high in case of fluorine atom as compared to chlorine atom in hydrogen chloride molecule. So to summarize, what are the factors affecting fluorine electronegativity in HCl? So in case of HCl molecule, atomic size increases, electronegativity decreases, shielding increases, electronegativity decreases, effective nuclear charge decreases, and electronegativity decreases. So what are the factors affecting fluorine electronegativity in hydrogen fluoride molecule? Atomic size decreases, electronegativity increases, shielding decreases, electronegativity increases, effective nuclear charge increases, and electronegativity also increases. So these factors govern or dictate the polarity of a molecule. That is the nuclear charge, atomic size, and shielding. And as a result, hydrogen fluoride molecule is more polar than hydrogen chloride molecule. So this is about these two molecules. But why is fluorine the most electronegative element in the periodic table? Let's find out. So let me explain the electronegativity concept in group 7 elements. Why only group 7 element? Because fluorine is a halogen and the most electronegative element in the periodic table. And it is assigned a value of 4 on the Pauling scale. The halogens, they have 7 valence electrons in the outermost shell and they are badly in need of 1 electron in order to complete the octet or to fill the outermost shell. Let me walk you through the factors affecting electronegativity in case of group 7 elements. So as you go down the halogen group, that is group 7, you will find the electronegativity value also decreases. So why the electronegativity value decreases as you go down the 7th group or the halogen group? So there are some factors which governs or dictates the electronegativity in the 7th group. Atomic size or atomic radii. Now as you go down the group, you will find the number of shells increase. As the number of shells increase, the distance between the nucleus and the outermost shell also increases. As the distance between the nucleus and the outermost shell increases, it decreases the electrostatic force of attraction between the positively charged protons and the negatively charged valence electrons. So the nucleus is losing its hold on the valence electrons as you go down the group. As a result, the electronegativity decreases. The second factor is electron shielding or shielding effect. So shielding is a phenomenon where the inner core electrons partially block or reduce the electrostatic force of attraction between the positively charged protons and the outermost valence electrons. So as you go down the group, you see that the number of shells increase. Now each shell acts as a shield. As the number of shells increased going down the group, the number of shields also increase. So each shell is acting as a shield, reducing the electrostatic force of attraction between the positively charged protons and the negatively charged valence electrons. And therefore the electronegativity decreases with increase in shielding effect. And what about the effective nuclear charge? So as the shielding increases, effective nuclear charge decreases. So effective nuclear charge is the electrostatic force of attraction between the positively charged protons and the outermost electrons, or the net positive charge experienced by the electron. So as the shielding increases, effective nuclear charge decreases, and thereby electronegativity decreases. And it's a general trend that with increase in the number of protons, effective nuclear charge will increase, obviously, and the electronegativity has to increase. But here, the shielding effect is winning over the atomic number. Though there is increase in the number of protons going down the group, it is the shielding effect which wins over the nuclear charge. And therefore, electronegativity decreases down the group. And the most important factor affecting the electronegativity is the stable electron configuration. So we know that halogens, they have only 7 valence electrons in their outermost valence shell, and they need to gain an electron in order to complete the outermost shell to achieve a full octet. So both fluorine and chlorine have 7 valence electrons, and they need to gain an additional electron to achieve a full octet. But electronegativity value is 4 in case of fluorine, while it is 3.2 in case of chlorine. Why is that? It is because of the factors what I have discussed. That is atomic size, shielding effect, effective nuclear charge, and stable electron configuration. So these 4 factors collectively contribute to a stronger or weaker ability of an atom to attract the shared pair of bonding valence electrons going down the group. So going down the group, you'll find that the atoms have a weaker ability to attract the shared pair of bonding valence electrons. So the attracting ability is more in case of fluorine atom as compared to chlorine atom because of the 4 factors: atomic size, nuclear charge, effective nuclear charge, shielding effect, and stable electron configuration. And that is why fluorine is the most electronegative element in the periodic table, and it has a stable electronic configuration. So if it gains 1 electron, it attains the stable electronic configuration. So when you compare and contrast the hydrogen chloride molecule from hydrogen fluoride molecule, you will find that fluorine, because of the factors what I have discussed so far, it attracts or pulls the shared pair of electrons closer to itself, leading to formation of a highly polar molecule. Now let me compare electronegativity of halogens with that of alkali metals. So I'll be comparing the electronegativity of group 7 with group 1 elements. And going down the group, the electronegativity decreases. Why is that? As you go down the group, electron shells or energy levels increase, atomic radius increases down the group, and with that electron shielding also increases, and this leads to decreased effective nuclear charge, and the end result is a decrease in the electronegativity values. You can see a decrease in electronegativity value starting from 4 with fluorine atom to 3.2 in chlorine and 2.8 in case of bromine atom. So well, in case of group 1 elements, that is alkali metals, you find a decrease in the electronegativity value as you go down the group. Now there is one highlighting feature which I need to mention here between these two groups is that halogens, they gain an electron to attain the stable electronic configuration of noble gases, while the alkali metals lose an electron to attain the stable electronic configuration of noble gases. So this is a highlighting and striking feature between the group 7 and group 1 elements. Group 7 element gains while group 1 element loses the electron to attain the stable electronic configuration. And they do so by engaging themselves in a chemical bonding. Now going across a period from left to right in the periodic table, you will find the electronegativity increases. So let me consider the period 2 elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So what about the number of protons for the period 2 elements? 3 in case of lithium, 4 in case of beryllium, 5 protons in boron, 6 in carbon, 7 in case of nitrogen, 8 for oxygen, 9 for fluorine, and total of 10 protons, nuclear protons in case of noble gas neon. So as you move across a period from left to right, you'll find that the number of protons increase. As the number of protons increase, you very well know that effective nuclear charge, that is the electrostatic force of attraction between the positively charged protons and the outermost valence electrons increases. And as a result, the atomic size increases. And not only that, it attracts or pulls the shared pair of electrons involved in chemical bonding closer to itself. And what about the number of shells? So as you move across a period from left to right, you will find that the number of shells are constant. So there is no change. Number of shells for period 2 elements is only 2. So therefore shielding is constant. And therefore the effective nuclear charge wins over the shielding in case of period 2 elements. And what about the number of valence electrons? Only 1 valence electron in case of lithium, 2 valence electrons in case of beryllium, 3 valence electrons in case of boron, 4 valence electrons in case of carbon, 5 valence electrons in case of nitrogen, 6 valence electrons in case of oxygen, 7 valence electrons in case of fluorine. And neon being a noble gas, it has a stable electronic configuration. It has achieved a full octet. The outermost shell is completely full with electrons. There is a total of 8 electrons. So atoms close to achieving a full octet will exhibit higher electronegativity. For example, fluorine. Now halogens or the halogen group, which is the 7th group, it's close to the 8th group, that is the noble gas group or the zero group elements. And that is why, so halogens, that is specifically about talking about a fluorine atom, it needs just 1 electron to complete the or to achieve the full octet. And therefore, it exhibits higher electronegativity with a value of 4 in the periodic, on the Pauling scale. So atoms close to achieving a full octet will exhibit higher electronegativity. And 4 will be the best example with a value of 4 on the Pauling scale. And what about the electronegativity? So the electronegativity increases as you move across a period from left to right. 1 for lithium, 1.5 for beryllium, 2 for boron, 2.5 for carbon, 3 for nitrogen, 3.5 for oxygen, and 4 for fluorine. And what about the noble gas neon? So there is no electronegativity value for noble gas neon. Why is that? Now neon is a noble gas with a stable electronic configuration. It neither gains electron nor loses electron, nor does it share any electron, because it does not participate in a chemical reaction. It is chemically unreactive. It's totally inert. And remember, electronegativity is a property of a bonded atom. So you can assign the electronegativity value to only those elements which are associated with another atom in a chemical bond. So electronegativity tends to increase as an atom gets closer to having a filled valence shell. And most importantly, electronegativity is a property that only occurs in atoms that are joined to another atom by a covalent bond, which the noble gases fail to do, and they do not participate in any chemical reaction, and therefore no electronegativity value assigned to the noble gases because of their stable electronic configuration. So these factors collectively contribute to a stronger ability of atoms to attract the shared pair of bonding valence electrons as you move across a period from left to right. So what are the factors governing the electronegativity across a period? The nuclear charge, the size of atom, shielding effect, and stable electron configuration. So all these factors collectively contribute. So it is not that one factor is governing the electronegativity of an element in the periodic table. So all these 4 to 5 factors collectively contribute towards its electronegativity in the periodic table. And that is why hydrogen fluoride has a higher electronegativity value, and therefore hydrogen fluoride molecule is more polar as compared to hydrogen chloride. So let me summarize the periodic trends in electronegativity. Going across a period from left to right in the periodic table, electronegativity value increases while the electronegativity value decreases going down a group from top to bottom. So as you move across a period from left to right, you will find the atomic size is decreasing. Number of shells are constant. So shielding is constant. And what about the number of protons? As you move from left to right in periodic table, the number of protons increase, and as a result, the effective nuclear charge increases, but not the number of shells. So as you move across a period, you'll find the effective nuclear charge is increasing, but not the shielding. Shielding is constant because the number of shells remain the same. That is only 2 shells in case of period 2 elements. So here the diagram representation is only for period 2 elements, showing the same number of shells across a period, that is only 2. So across a period for the period 2 elements, shells are constant, only 2 shells. Effective nuclear charge is increasing but not shielding. Valence electrons increase as you go across a period, and as the atoms are approaching towards the noble gas group, they are very close to the octet. And that is to say, they are very close to achieving the octet, filling their outermost shell. And therefore, the electronegativity value increases across a period as you move from left to right. So electronegativity tends to increase as an atom gets closer to having a filled valence shell. So atoms close to achieving a full octet exhibit higher electronegativity. So beryllium has electronegativity value of 1.5, boron 2, carbon 2.5, nitrogen 3, oxygen 3.5, and fluorine 4. And fluorine is very closer to achieving a or having a filled valence shell, and therefore it exhibits higher electronegativity. And apart from that, there are other factors, associated factors like size, atomic size, nuclear charge, that is affecting nuclear charge, and shielding, which is favoring the fluorine atom. And that is why hydrogen fluoride molecule is more polar as compared to hydrogen chloride molecule. And going down the group, you see the number of shells increase. As the number of shell increases, the size of the atom increases, and this leads to increased shielding. And what about the number of protons? Though the number of protons increase, the shielding effect wins over the effective nuclear charge or the number of protons. So as you go down the group, shells increase, the size of the atom increase, the number of electrons, inner core electrons increases. This leads to shielding, increase in shielding, and effective nuclear charge goes down, and finally the end result is the electronegativity value decreases as you go down a group. Don't forget to subscribe my channel, share and like my videos. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.